Back to the Comptia Network Plus course. STP Convergence. Convergence is what happens when all ports on the bridges and switches have transitioned to either forwarding or blocking modes. During this phase, no data will be forwarded until the convergence event is complete. Before data can begin being forwarded again, all devices must be updated. When STP is converging, all the host data stops transmitting. So if you want to remain on speaking terms with your network users or remain employed for any length of time, you positively must make sure that your switch network is physically designed really well so that STP can convert quickly and painlessly. Figure 1112 demonstrates a really great way to design and implement your switched network so that STP converges efficiently. Convergence is truly important because it ensures that all devices are either the forwarding mode or blocking mode. But as I've drilled into, it does cost you some time. It usually takes 50 seconds to go from blocking to forwarding mode, and I don't recommend changing the default STP timers. You can adjust those timers if you really have to. By creating your physical switch design in a hierarchical manner as shown in figure 1112, you can make your core switch the STP route. This makes everyone happy because it makes STP convergence happen fast. Because the typical spanning tree topology's time to convergence from blocking to forwarding on a switch port is 50 seconds, it can create timeout problems on your servers or hosts, like when you reboot them. To address this hitch, you can disable spanning tree on individual ports. So a rapid spanning tree protocol 802.1w. How would you like to have a good STP configuration running on your switch network regardless of brand of switches, but instead of taking 50 seconds to converge, the switch network can converge in about 5 seconds or maybe even less? Or STP was not designed to be a brand new protocol but more of an evolution of the 802.1d standard, with faster convergence time when a topology change occurs. Backward compatibility was a must when 802.1 was created. The 802.1w is defined in these different port states compared to 802.1d. Disabled discarding, blocking discarding, listening discarding, learning forwarding. To verify the spanning tree type route running on your Cisco router, use the following command: s1 # spanning tree VLAN 0001 spanning tree enabled IEEE route priority 32769 address 000d.2 bd.4b80 cost 312 port 56 port channel 1. Hello 2 sec max H20 C forward delay 15 sec. Bridge priority 49153 preparatory 49152 sys ID ext1 address 001b.2b55.7500. Hello time 2 sec max age 20 sec forward delay 15 sec adding time 15 uplink fast enabled. Interface role STS cost prior NBR type FA0/3 DSG forward 3100 128.3 edge SHR. FA0/4 DEG forward 3019 128.4 edge P2P. FA04/8 designate forward 3019 128.8 P2P, I suppose peer-to-peer. P01 route forward 312 128.56 peer-to-peer. Since this type of output shows spanning tree protocol, IEEE, we know we are running the 802.1d protocol. If the output shows RSTP, then you know your switch is running the 802.1w protocol. Virtual LANs. By default, switches break up collision domains and routers break up broadcast domains. In contrast to the networks of yesterday, which were based on collapsed backbones, today's network design is characterized by a filter architecture thanks to switches. So now what? How do we break up broadcast domains in a pure switched internetwork? By creating a virtual local area network, VLAN. A VLAN is a logical grouping of network users and resources connected to administratively defined ports on a switch. When you create VLANs, you gain the ability to create smaller broadcast domains within a layer 2 switched internetwork by assigning the various ports on the switch to different subnetworks. A VLAN is treated like its own subnet or broadcast domain, meaning that frames broadcasted onto the network are treated like its own subnet or broadcast domain, meaning that frames broadcasted onto the network are only switched between the ports logically grouped within the same VLAN. So does this mean we no longer need routers? Maybe yes, maybe no. It really depends on what your specific goals and needs are. By default, hosts in a specific VLAN can't communicate with hosts that are members of another VLAN. So if you want inter-VLAN communication, the answer is yes, you still need a router. VLAN Basics. Figure 11.3 shows how layer 2 switched networks are typically designed as flat networks. With this configuration, every broadcast packet transmitted is seen by every device on the network regardless of whether the device needs to receive that data or not. By default, routers allow broadcasts to occur only within the originating network, whereas switches forward broadcast to all segments. Oh, by the way, the reason it's called a flat network is because it's one broadcast domain, not because the actual design is physically flat. In figure 11.3, you can see host A sending out a broadcast and all ports and all switches forwarding it, all except each port that receives it. Now check out figure 11.14. It pictures a switched network and shows host A sending a frame with host D as its destination. What's important to get out of this figure is that the frame is forwarded only out of the port where host D is located. This is a huge improvement over the old hub networks. Unless having one collision domain by default is what you really want, you already know that the coolest benefit you gain by having a layer 2 switch network is that it creates an individual collision domain segment for each device plugged into each port on the switch. But as is often the case, new advances bring new challenges with them. One of the biggest is the greater number of users and devices, the more broadcasts and packets each switch must handle. And of course, the all-important issue of security and its demands also must be considered while simultaneously becoming more complicated. VLANs present a security challenge because by default, within the typical layer 2 switched internetwork, all users can see all devices. And you can't stop devices from broadcasting. Plus, you can't stop users from trying to respond to broadcasts. This means your security options are dismally limited to placing passwords on your servers and other devices. To understand how a VLAN looks to a switch, it's helpful to begin by first looking at a traditional network. Figure 11.15 shows how a network used to be created using hubs to connect physical LANs to a router. So here you can see figure 11.15. Here you have engineering, hubs, and engineering, sales, shipping, marketing, finance, and management. Here you can see that each network is attached with a hub port, here you can see each network is attached with a hub port to the router. Each segment also has its own logical network number, even though this isn't always looking from the frame. Each host attached to a particular network has a match that network's logical network number in order to be able to communicate on the internetwork. Notice that each department has its own LAN, so if we need to add new users to, let's say, sales, we would just plug them into the sales LAN and they would automatically be part of the sales collision and broadcast domain. This design actually did work well for many years, but there was one major flaw. What happens if the hub for sales is full and we need to add another user to the sales LAN? Or what could we do if there's no more physical space for new employees where the sales team is located? Well, let's say there's just happens to be plenty of room over in the finance section of the building. The new sales team member will just have to sit on the same side of the building as the finance people and will just plug the poor soul into the hub for finance. Simple, right? So wrong. Doing this obviously makes a new user part of the finance LAN, which is very bad for many reasons. First and foremost, we now have a major security issue because the new sales employee is a member of the finance broadcast domain. The newbie can see all the same servers and access all network services that the finance folks can. Second, for this user to access the sales network services, they need to get their job done. So they would have to go through the router to log into the sales server. Not exactly efficient. Now let's look at switch accomplishes for us. Figure 11.16 demonstrates how switches come to the rescue by removing the physical boundary to solve our problem. It also shows how 6 VLANs numbered 2 through 7 are used to create a broadcast domain for each department. Each switch port is then administratively assigned a VLAN membership depending on the host to which the domain is placed in. So here's figure 11.16. So now if we need to add another user to the sales VLAN 7, we could just assign the port to VLAN 7 regardless of where the new sales team member is physically located. This illustrates one of the sweetest advantages to designing your network with VLANs over the old collapsed backbone design. Now cleanly and simply, each host that needs to be in the sales VLAN is merely assigned to VLAN 7. Notice that I started assigning VLANs with VLAN number 2. The number is irrelevant, but you might be wondering what happened to VLAN 1. Well, that VLAN is an administrative VLAN, even though it can be used for a workgroup. Cisco recommends that you use it for administrative purposes only. You can't be used for a workgroup. Cisco recommends that you use it for administrative purposes only. You can't delete or change the name of the VLAN 1. By default, all ports on a switch are members of VLAN 1 until you actually do change them. Now, because each VLAN is considered a broadcast domain, it's got to also have its own subnet number. Refer again to figure 1116. And if you're also using IP version 6, then each VLAN must also be assigned its own IP version 6 network number. So you don't get confused, just keep thinking of VLANs as separate subnets or networks. Let's get back to that because of switches. We don't need routers anymore. Misconception. When looking at figure 11.6, you can see that there are 7 VLANs or broadcast domain, counting VLAN 1 not shown in the figure. The hosts within each VLAN can communicate with each other, but not with anything in a different VLAN, because the hosts in any given VLAN think they are actually in a collapsed backbone, illustrated in figure 11.15. So what handy little device do you think we need to enable the hosts in figure 11.6 to communicate to a host or hosts on a different VLAN? You guessed it, a router. Those hosts absolutely need to go through a router or some other layer 3 device, just as they do when they're configured for inter-network communication as shown in figure 11.15. It works the same way it would if we're trying to connect different physical networks. Communication between VLANs must go through a layer 3 device. So I'm going to leave it here today for this video. If you liked listening, please consider sharing and subscribing. Thank you.